So suppose we have this function, f of x, y, and z equal to square root of 16 minus x squared minus y squared minus z squared. This is a function from three-dimensional space to R. In the homework, we have a similar question, which I asked you to sketch the level surfaces of F for, say, z equal to 1, 2, and 3. So you should say z is equal to this function, f. Maybe I should use another variable, I'm sorry, say w. You should say w is equal to this function f of x, y, and z, which is square root of 16 minus x squared minus y squared minus z squared. Now, if I square this function, w squared would be equal to 16 minus x squared minus y squared minus z squared. If w is 1, we would get 1 is equal to 16 minus x squared minus y squared minus z squared, which means x squared plus y squared plus z squared equals to 15. Well, if I want to sketch this surface, it means I should look at the three-dimensional space. It would be the sphere centered at the origin with radius square root of 15. So it would be this sphere here. The radius is square root of 15. If I want to look at the level surface of 2, it means 2 squared, which is 4, is equal to 16 minus x squared minus y squared minus z squared. Therefore, x squared plus y squared plus z squared equals to 12. So we would have a surface. The surface we have here is a sphere centered at the origin with radius square root of 12. And finally, if we let w to be 3, w squared is 9 equals to 16 minus x squared minus y squared minus z squared. And therefore, x squared plus y squared plus z squared is equal to 7. Therefore, inside this sphere, we have smaller sphere with radius square root of 7. Now, if you want to sketch it using this website, 3D plots, what would happen is that, well, these surfaces, each of them kind of contains the other one, you see? So we wouldn't really see these surfaces. They are inside each other. So how can we sketch it so that we can see these surfaces? We can really see them. That's the point, okay? So that's what I want to explain to you, 3D plot surfaces. Okay, so let me show it to you. Okay, now here we have 3 surfaces, right? So we have 3 surfaces. If we compute z in each case, if I compute z, it would be, well, the square root of 16 minus x squared minus y squared. Well, 16 minus 1, the first one was 15. Square root of that. So okay, and let's say the range is minus 10 to 10, minus 10 to 10. Okay, that would be, that's one semisphere. We can copy the same thing here with the negative sign to get the other part. And let's give it the range for x and y. That's what would we get, right? Now inside this sphere, we have another sphere. When we are sketching the level surfaces, we should do it for, we should sketch the other spheres too, right? The other sphere was 16 minus 4, which is 12. So we have the other sphere inside this one, and it's negative. But now the point is that we can't see the other sphere because the other sphere is inside this one. So if I see, you can see this is the other sphere, but there is this sphere which contains the other one. How can I see? How can I see both of these surfaces at the same time? You know, the point is that if you click on this symbol here, well, cut off 1/2 is one way, but we like to see the surfaces completely. So if you look at this notation here, I'm showing you, there is a dot inside something like a sun. If you click on that, there is something called transparency. I can move the transparency. I can bring the transparency down here. So say 45. Something around 45, 43. I can do this for this one too. So as you can see now, I can see both of these surfaces. Now I can make the surface inside also a little bit transparent. So let's put it on, say something around here. Say around 100. It is still transparent, but less than the one we have outside. So we can still recognize them, right? And then there is, well, we were supposed to sketch it for 3 different values. Let's do it for maybe I change the number of grids too. It might be helpful to see it better. Or worse, actually. Maybe 30 was better. Or maybe even 20. Okay, that's what we would see here. We have these 2 surfaces. Maybe, well, yeah, that's good. So now there is another one, another surface we have inside these 2 surfaces. So one of them was 16 minus, what was the last one? 16 minus 9, it was 7. And minus 7. And then say the range is from minus 10 to 10 for 20, or maybe for 30 grid lines. And minus 10 to 10 for 30 grid lines. So as you can see now, in some sense, we can see all of these 3 surfaces in just one 3-dimensional space. In R3, we can see all of them. So that's the idea, using different transparencies to see all of these things. Maybe I can make this out, the one which is completely on the outside, completely transparent, like this. So I have this transparent surface outside. I have the first surface which is almost transparent, the inside, and one surface finally in the middle. So this is a way to see all of these surfaces at the same time. And you should do this in your homework. So one more time, see if you click the bottom here, the icon here would give you transparency, and you can change these things. So there are other options too. I'm not sure exactly what these options do. Okay, this is not good. Hide the edges. That's not also good. Well, anyway. Anyway, this is the way to do it. Okay. Let's go back to gradients. This is the last topic I'm going to talk about today. So again, suppose we have a function f from, say, R2 to R. So f takes two values, x and y. The gradient of f, which I use this notation to show it, which sometimes it's called nabla f, is just a vector where the first coordinate of this vector is partial derivative of f with respect to x, and the second coordinate is partial derivative of f with respect to y. Well, if f was a three-dimensional function, a function defined in three-dimensional space, which takes three values, x, y, and z, gradient of f is defined to be a vector in three-dimensional space, which the first coordinate is partial derivative of f with respect to x. The second coordinate is partial derivative of f with respect to y. The third coordinate is partial derivative of f with respect to z. Okay. So it's simple. Well, let's look at a few examples. Let's say f of x and y is equal to y squared plus x ln of y. And so what is gradient of f? Well, we should take derivative with respect to x. It would be ln of y. Because if you are taking derivative with respect to x, y is a constant. Therefore, ln of y is a constant. It's constant coefficient of x. If you are taking derivative with respect to x, the derivative would be just that coefficient, which is ln of y. And then I should take derivative with respect to y. Well, the derivative with respect to y of the first term is 2y. And derivative with respect to y of the second term is, we have this constant coefficient, derivative of y would, ln of y would be 1 over y. So this is the gradient of f. Also, similarly, if we have a function with three variables, let's say x squared y plus sine of z, the gradient of the function would be the derivative, the partial derivative with respect to x, which is 2xy, the partial derivative with respect to y, which is x squared, and the partial derivative with respect to z, which is cosine of z. So that would be the gradient of this function. Now, this gradient is related to things we've seen before, actually. This gradient is something which has, for functions from, say, Rn to R, or R2 to R, or R3 to R, for these functions, this gradient is something which has the information of all directional derivatives inside it. So you see, I talked about the directional derivative of f in direction of u, where u is cosine of theta, sine of theta. I told you it is, well, one way to compute it is taking partial derivative of f with respect to x, multiplied with cosine of theta, plus taking partial derivative of f with respect to y, multiplying it by sine of theta. This is actually the inner product of these two vectors, partial derivative of f with respect to x, partial derivative of f with respect to y, dot product, or the inner product, with cosine of theta, sine of theta. But what is this vector, partial derivative of f with respect to x and partial derivative of f with respect to y? Well, this is the gradient of f. What is cosine theta and sine theta? Simply u. Well, we get to this very, very important formula. the directional derivative of f in direction of u is gradient of f dot u. Okay, now someone has asked, what does this thing mean geometrically? And that's pretty interesting, actually. This turns out to have a very good answer. Go back to the question of the hill, the mountain, if you have a mountain here. Okay, suppose we have at a point x, y here, and if we look at the function about xy, we have someone there. At each point, we can look at, take z for f of xy to be the value of the function above that. So we have a person there. Now look at the direction, which if you walk in that direction, you have the maximum slope. So for example, here, if this person goes towards this direction, the height would change at most. That would be the direction, which if the person walks in that direction, the height would increase the most, or this person in this direction. So the direction here, suppose it's x and y, this would be the direction which if this guy goes into that direction, the height would increase the most. The gradient of the function is actually that direction. The gradient of the function is the direction which f increases the most, if that person walks into that direction. Okay, someone wants to see this slide again. Also, I can say you can see that here too. You can prove what I said using this formula. I wouldn't do that, but it's not hard to do. We can use this to show the gradient of f is actually the direction, which if you go into that direction, f would increase the most. Okay. Now, I can just, to see this thing again, repeat this thing one more time. Suppose we have a function f of x and y equals, say, x squared plus 2y squared. Suppose I want to compute the directional derivative of f in direction of u, where u is this direction. The direction, say, cosine of pi over 4, sine of pi over 4. Okay, I want to use this formula again. So derivative of f in direction of u, directional derivative of f in direction of u is equal to the inner product of gradient of f with u. Okay, what is gradient of f? Gradient of f is partial derivative of f with respect to x, partial derivative of f with respect to y, inner product with u, which is cosine of pi over 4, sine of pi over 4. What is partial derivative of f with respect to x? It's 2x. What is partial derivative of f with respect to y? It's 4y. Cosine of pi over 4 is the square root of 2 over 2. Sine of pi over 4 is the square root of 2 over 2. If I multiply them, I would get square root of 2x plus 2 square root of 2y. So for example, if we were to compute this thing at some given point, say, I don't know. So if they asked us to compute it at the point 0 and 1, it would have been square root of 2 times 0, which is 0 plus 2 times the square root of 2 times 1, which is 2 square root of 2. So this is another way of thinking about the directional derivative and gradients. Okay, so there are a few things, a few kind of properties of the gradient. So properties of the gradients. One, it would give you, as I said, this, the gradient of f is the direction f increases the most. Well, it gives something us immediately. Negative gradient of f is the direction f decreases the most. So if you are on a mountain, if you are here, if you go in that direction, the height would increase the most. If you go to minus that direction, which, well, actually the direction should be plotted in R2. If you go into the blue direction, the height would decreases the most. If gradient of a function is 0, it means duf would be 0 times the inner product of 0 with any vector u, which would be 0 for any direction. So if gradient of a function is 0, it means the directional derivative in all directions are 0. So if the gradients, therefore, if the gradients of a function at a given point is equal to 0, it means directional derivative is 0 in all directions. Okay. That's one other thing. 3. So what is the maximum value of directional derivative? What is the max of directional derivative? Could you show a graph where gradient is always 0? Always 0. If the gradient is 0 at every point, it means the function is constant. But for example, if you look at a mountain, the gradient would be 0 at the peak. Well, because here the slope in both directions are 0. So the gradient would be partial derivative of f with respect to x and partial derivative of f with respect to y. Say these are these two directions. And because the slope is 0 at both of them, we would end up with 0 and 0. Okay. So what is the maximum of directional derivative? Well, as I said, the directional derivative is equal to gradient of the function inner product with the direction u. But actually, this, as I said, this is going to be the directional derivative. The change would be maximum if we exactly go in direction of f. But there is a small mistake here. The gradient of the function might not be unit. We are always assuming u is a unit vector. So I should make this unit. I should divide it by its length. If I do that, it would be a unit vector. So the maximum of directional derivative would be gradient of f, inner product with gradient of f over its norm. But what is that? Well, it would be gradient of f inner product itself, so it would be gradient of fx squared, its norm squared over its norm, which is, well, just the norm of gradient of f. So for example, if we have a function, say f is equal to x squared plus y squared, at some point, say x and y equal to 0 and 1, if they ask us what is the max of directional derivative of f in any direction, what is the max? We should say the max is equal to the norm of gradients, which is the norm of this vector, derivative of f with respect to x, which is 2x and 2y. At that point, which is, at this point, this is equal to 2 and 0. And the length of this thing is 2 squared, which is 4, plus 0 squared, which is the square root of 4, which is 2. So at any point, the maximum of directional derivative is equal to the length of this vector gradient of f. We have a question. How does gradient being the direction in which f increases the most related to gradient vector with the partial derivatives? Okay, you can use, well, I mean, you can use this formula. Okay, I can explain this a little bit more. So as I said, the derivative of f in direction of u is equal to gradient of f inner product with u. But remember, inner product is equal to the length of the first vector times the second vector times cosine of theta. Okay, where cosine of theta is the angle between these two vectors. Now, when is this inner product, when is it maximum? When is inner product max? Well, cosine of theta is always less or equal than 1. It's max when it's equal to 1. So if theta is 0, we would have maximum thing we would get, which would be partial, which would be the gradient vector times norm of u times 1. That's the maximum value of cosine of theta. But theta being 0 means the angle between u and gradient of f is 0. So it means u and gradient of f are in the same direction. So f would increases the most if u is in direction of gradient of f. So wait, so u is always equal to f over norm of f star f? I guess you mean by that, you mean gradient of f? No, I'm saying the directional derivative would be maximized if u is equal to this thing. Not that it is always equal to that. If you walk in this direction, you would feel the height of the mountain is increasing the most. So it doesn't mean u is always equal to that. U can be any direction. But this is the direction which f would increase the most if you walk in that direction. Okay. Let's look at a few more examples. Okay, suppose we have a metal plate, something like this. Suppose we have a metal plate. And each point of this plate has some temperature. Okay. Suppose I have x and y directions here. And the temperature at the point x and y is given by, suppose a formula, 20 minus 4x squared minus y squared. So at any point x and y, using this formula, I can compute the temperature at that point. Now, the question is, suppose you are at this point. Suppose not in this given point, actually. Suppose we are looking at this point 2 and minus 3, which is here. 1, 2, 1, 2, 3. We are at this point, say point P. Now, the question is, in what, suppose there is an ant here. The ant looks like a human for some reason. In what direction the ant should walk, which the temperature would increase the most? So in what direction the ant should walk, which the ant would feel the temperature is increasing the most? Okay. The answer is, well, the temperature would increase the most in direction of gradient of this thing, which is derivative of t with respect to x, derivative of t with respect to y. Well, what is derivative of t with respect to x? It's minus 8x. What is derivative of t with respect to y? It's minus 2y. X is equal to 2, it would be minus 16. Y is minus 3, would be 6. So it would be this direction. This is the vector which it should walk in direction of that vector. so the temperature would increase the most. Okay. Okay. So there is one more fact I want to mention here. Fact. If we have a function f from R2 to R, say f of x and y is square root of, say, 4 minus x squared minus y squared. We could look at its level curves. Right? For example, let's say we want to look at level curves where the values of z equal to 0, 1, yeah, 0, 1, and well, maybe I can change 4 to 9 to make it a little more interesting. 0, 1, and 2. Okay, so I should say z is equal to square root of 9 minus x squared minus y squared. I can say z squared is equal to 9 minus x squared minus y squared. Therefore, x squared plus y squared plus z squared equals to 9. Now, if z is 0, it means x squared plus y squared equals to 9. It means I have the circle with radius 3. If z is 1, it means x squared plus y squared plus 1 equals to 9. If I take 1 to the other side, it would be equal to 8. It means I have a circle with radius square root of 8. And if z is 2, x squared plus y squared plus 4 would be 9. I take 4 to the other side. 9 minus 4 would be 5. It means I have a circle centered at the origin with the radius square root of 5. Now, there is something quite important, especially in physics. If we look at the gradient vector of the function f at each point, say I'm looking at it at this point, it would definitely, it's gonna be normal to the level curve. So at this point, the gradient vector would be something like this. For example, at this point, it would be something like this. It would be always normal to the direction of the level curve. So if you have another function which they tell us its level curves looks like this, if they tell us at this point, what would be the gradient of the function f? It would be either at this direction or at this direction. It would be normal at this line here. Or if they tell us what it's going to be here, it's either going to be this direction or that direction. It's always orthogonal to the level curves. That was the fact I wanted to mention. Now we have the same thing for 3 variables. It's completely similar. So the gradient of a function with 3 variables would be the partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z, and directional derivative of f in direction of u would be again the inner product of the gradient and with u. But remember, in 3-dimensional case, u should be a 3-dimensional vector, say a, b, c. There is no way of writing it as but we don't write it as cosine of theta, sine of theta like that anymore because it should have 3 components. But still, we would assume it's unit vector. What does it mean to be unit vector? It means its length should be 1. What is its length? It's a squared plus b squared plus c squared. Its square root should be 1. If we square that, it means a squared plus b squared plus c squared should be 1. So the unit vectors in R3 are of the form A, B, C. where a squared plus b squared plus c squared is equal to 1. And everything else is similar. There is no difference between this and the more general case. Okay, I don't want to continue teaching here. This was the end of section 13.6. On Thursday, I would start the section 13.7. No, sorry, that's not true. I'm not gonna talk about section 13.7 actually. I would skip that. That's not really important for our purposes. I would talk about section 13.8, which is about extrema, or max or mean of functions of two variables. So just to mention, I've explained the syllabus to you earlier, but just to mention one more time, on Thursday, I'm going to finish this chapter 13, and I would start chapter 14. And next week, I will finish chapter 14. So, which is about multiple integration. So that's enough for today. I will be here if you have any question about the homework or anything from the exam or anything like that we can discuss. Also, I would upload the grades of the exam by Thursday. Okay, so that's it for today.